I'm just gonna get right to it. So in my last video, I shared about my internship here in the University of Tokyo, and I ended up flailing around basically and not getting the nanofibers that I wanted, which was my main research project, to get those nanofibers. So I took another approach, or at least I tried. See, there's a lot of factors that come into getting those nanofibers or not. There's temperature, there's humidity, and there's also needle diameter, on top of other things I've mentioned in my other video. So these specific ones about the temperature and humidity, those don't really get reported in papers that do electrospinning, and that's kind of the problem. See, I used different voltage values, different distance values from different papers, so I was making combinations of those factors that weren't appropriate, basically. See, the thing is that when these researchers do these experiments on electrospinning, they have to optimize the conditions to get those nanofibers, because from lab to lab, the temperature, humidity stuff, it's different. So what would happen is that they would take a lot of trials to finally get those nanofibers. My predicament is that the solution I'm using to put through that electrospinning process is pretty hard to get. It's kind of expensive, and it takes a while for it to get here. You know, it comes all the way from Germany, so that's not really practical for me to order every time I want to conduct more and more of those trials. Of course, it's a science thing that you have to do things again and again, but is there some way where you kind of get to cut through all that, where you don't have to do too much of these trials? You know, where's that sweet spot, and how do I know that this is the number of trials that I need to do? That's the priority question I had in order to get those nanofibers. So quick intro on why I'm trying to do this electrospinning thing is because there's this biodegradable plastic alternative that researchers are working on. It's called polylactic acid. That's basically starch, the starch molecules that you have from bread or corn or whatever carbohydrate you can think of, and you can turn that into a polymer by some processes that I will not get into right now, because that's going to be a lot of confusing stuff for now. But the thing is that this plastic alternative is biodegradable, yes, but it doesn't really compete with regular plastic that we have in terms of how strong it is. So this one that I'm trying to work on, which is called PLA, it's kind of flimsy basically. And what I want to do is put this solution containing this PLA through electrospinning, because what electrospinning basically does is that you apply a voltage through that solution, and that voltage forces the solution to come out of a needle and form jets, basically spider webs of the solution. And if you happen to have a sheet where that solution can be sprayed on, you come up with a material, a sheet basically, that is made of those spider webs of PLA. And those structures, those nanofibers in that jet, are supposed to make the PLA stronger. So it's supposed to be able to compete with the strength of normal plastic. So that's basically what I'm trying to do. But it is hard to get the solution out to form the proper shape of jets coming out, because sometimes you're using the wrong voltage, or it's too high, the needle, it's too high from or too far from the sheet where you want it to be sprayed on, and you don't come up with the smooth jet that you want. And yeah, so that's what I'm trying to fix. So what exactly did I do? So if I were to wrap everything up in one single line, it's how do I deal with something that is complex and messy? You can do the systematic thing, which is, since there are a lot of factors, right, you can just change one by one. You can change the values for each of those factors one by one and keep everything else the same, and then move on to the next factor and change that value and keep everything else the same. But then again, as I said earlier, this is going to be really time consuming. So imagine the number of trials I have to do for each factor that I change. You can't just do 5. I don't think that's enough, personally, based on what I did. And imagine that there are 6 factors, so just counting all of that, that's already 30. So what do? Here comes machine learning, which, to be honest, is just linear fitting on drugs. This way, given experiments that ran on different humidities and temperatures, we can generalize a Goldilocks zone for getting those nanofibers. So because there are different conditions for each of those experiments, there must be that average for the things that we can control. So those things that we can control are the things like the voltage, the needle diameter, and the distance between the tip and the sheet. Things like temperature we can, but it's pretty difficult to do so. So for example, what if you're doing experiments in the winter and your data set is fitted for kind of winter experiments, and then you want to do the same thing in the summer, but then you only have data set for the winter, so you have to do everything again. There are a lot of ways to optimize things. So there are a lot of methods in machine learning, and they have their own pros and cons and all that, and that there will always be disclaimers for each one of those. So which machine learning method are you supposed to use on this kind of data set, that kind of stuff. And the other thing is that machine learning isn't this mystical thing that will solve everyone's problems. I mean, in fact, there's this huge ass disclaimer about the ethics of using artificial intelligence, about using AI. I mean, can you believe it? There's ethics of using equations, right? I mean, it's kind of interesting, and I will talk about this thing because it's really important. The social aspect of doing science is really important, so I will include this later on. So I read these 2 papers. One of them is about electrospinning a polymer, another polymer, PVDF, and the other is about crystallizing PLA. I couldn't find a paper on electrospinning PLA because, it's not really something a lot of people do, but as a starting point, that paper about electrospinning PVDF may be a good introduction for me to understand how I may use the other solution, PLA, through this machine learning method. So we just want to see how values like the solution's concentration, electrospinning voltage, and tip to collector distance affect the nanofibers we get. So specifically, we look at the average diameter of beads, how big they are, or if there are nanofiber defects, like are there other shapes present, and there's also how different these beads could be from each other. Some of them are a little big, some of them are a little small, and then there's how much there are in a specific amount of space. So respectively, if you want to kind of have a shorthand for all of these terms, we're just going to use BMed, SDev, and BD from now on. So these 2 papers started by synthesizing their own stuff and using that data to come up with models based on machine learning algorithms. Bro, what the fuck does that mean? So for example, in the electrospinning paper, they made 126 plates of PVDF nanofibers, all with different values for the concentration, voltage, etc. These 126 plates are put under a microscope, and from the images of the samples, we can measure the diameter, the density, and all that crap, those BMed, SDev, and BD I told you about earlier. Okay, so now we have 2 sets of data, what we adjusted and what we observed. We want to optimize those things we observe. Okay, in some cases, we want 0 beads. We want none of those defects. And sometimes we want thinner nanofibers. The question is, what concentration voltage values do we need to get 0 beads, to get super thin fibers? By using the data we have, we can relate how these affect each other and use that as a guide to get whatever kind of fibers we want in the future. We have this web of data where we know this affects this or this affects this, but how much do they affect each other is what we have to know. So these relationships aren't simple. In some cases, we need to square the concentration value, while some factors have less weight. In other words, they don't really affect how the nanofibers come out. So exactly how do we determine those relationships? This is how those algorithms come in. An algorithm is just a set of orders that a computer follows to try to fit all the data we gave the computer to get a single equation or model that represents all our data points. So all of our data points get condensed into this one equation. Isn't that neat? But can this motherfucker be a little more concrete though? So how exactly do you start? So the general practice is that you start with random relationships between our input and output values. So we take our input, plug it into our model equation, into our guess, and see how far the answer is from this guess from the actual value. And from looking at this difference, we can adjust our equation. In other words, we're learning. Basically, if you weigh something and you need this specific amount, and you can see that the measurement that comes out of the scale is bigger, of course you take stuff out, or vice versa. When there's too little amount of stuff in the scale and you want more, obviously you add more. That's basically the idea. And how much you try to take out of your sample when you're weighing this thing, how much you do that every time you're trying to correct value, is essentially the kind of flavor of algorithm you have. So some algorithms take like huge changes in order to try to get to that correct value. Some of them like take really small steps to get there. Sometimes they take convoluted jumps where you take some stuff out, you take an excess out, and then you put 2 in, and then you see if that gets near the value, okay, and then you take some out again. It's kind of convoluted. Sometimes it's like that. And I'm gonna have to cut the video here because the entire point of this part 1 is just to set up everything, get rid of the vagueness that comes with machine learning. Time and time again, I will say machine learning is not some magic tool that will fix everything, because it's really not. So I will say this again and again until that shit sinks in. And if you want more specifics on those algorithms, on those machine learning methods, watch my next video. So thanks for watching. I'll see you next time.